Today our topic is differentiability of a function. When can we say that a function is differentiable? Now, function, a real valued function, real valued means the values are real. The functional values at each and every point in its domain of definition are real. So, a real valued function f of x is said to be differentiable at x is equal to c if at a particular point c in its domain of definition we can say that the function is differentiable if and only if the left hand derivative is equal to the right hand derivative. Left hand derivative means the limit x tends to c minus f of x minus f of c by x minus c, and right hand derivative means limit x tends to c plus f of x minus f of c by x minus c. And now you see x tends to c minus, that is the value of x is smaller than c. How much smaller? Let it is h, and in this case how much greater? X tends to c plus, that means the value of x is greater than c. How much greater? Let it is h. That means that h is a very small value. Let that h tends to 0. Okay. So if h tends to 0, so this x will be c minus h. Put c minus h instead of x here. What we will get? Limit h tends to 0. F of c minus h minus f of c by c minus h minus c, that means plus c and minus c will be eliminated, we will get minus h. And similarly here if we replace x by c plus h, then what we will get? Limit h tends to 0, f of c plus h minus f of c by h. That means a function f of x is said to be differentiable at the point c if the left hand limit h tends to 0, f of c minus h minus f of c by minus h is equal to limit h tends to 0, f of c plus h minus f of c by h. If this one is satisfied, then only we can say that the function f of x is differentiable at x is equal to c. In this process, we just checked the differentiability of a function f of x at a particular point c. Now, if the function is defined in the closed interval AB, suppose it is defined in closed interval AB, then what can we say about the endpoints? That is, at the point A, how can I say that at A it is differentiable? Now, at the point A, you see it is the left side. Okay, that means the interval, the domain started from A. At the point A, the function f of x is only right hand differentiable, and at the point B it is only left hand differentiable. Okay, if the function is given defined in the closed interval AB, that means a function is derivable in its closed interval if it is derivable in that open interval. I am telling again, that is a function f of x, it is differentiable in the closed interval AB if and only if it is differentiable in the open interval AB. Now you see the graphs. In the first case, it is a linear function. It is always differentiable. That means for all values of x in its domain, it is differentiable. If a curve like this, it is also derivable for all values of x in the domain of its definition. But you see, if there exists any point, any peak point like this, okay, in these points the function will not be differentiable. Why? We will get two different values of left hand derivative and right hand derivative. That means the value of left hand derivative and the right hand derivative are not same in these points, like these peak points. So here the function is not differentiable. Here in this function there are 2 points where the function is not differentiable. Okay, now in all these four graphs you can see the function are continuous. Here it is continuous, derivable. Here it is continuous, derivable. Here also the function is continuous but not derivable. Here also the function is continuous but not derivable. That means continuity, it is a necessary condition but not sufficient. That means every derivable function are continuous but all the continuous function are not derivable. I repeat, every continuous function are derivable but every derivable function are continuous but all the continuous function are not derivable.